Okay, so now we have Mercè Guerrero from Avail University, and Mercè is going to talk about the optical appearance of spherical objects. So, floor is yours.
Well, thank you very much. I hope that you can hear me well. Okay. So first, I would like to thank the organizers, and it's a pleasure to be here for the first time. Today, I think that I would do a rather pedagogical talk about optical appearance of static spherically symmetric objects. So the thing is that when we analyze the optical appearance, we have basically two contributions, the geometry and the disk. So from the one side, the background geometry, it's only responsible from the critical curve, the light rim. But on the other hand, this optical appearance, it's also very depending on the accretion disk and the properties that we add to this. So if it's optically thin or optically thick, and if it has some width or not. And the thing is that actually in some papers it was already discussed that there's an untangling between these two contributions. So it can be difficult to know if some feature of the image is due to geometry or due to also this creation disk. So yeah, the thing is there any way to be able to disentangle these two contributions? So for this, we are going to, I'm going to present here three objects or three geometries that we studied in several works with, sorry, I forgot to mention, but Gonzalo Olmo, Diego Rubiera, and Diego Sainz. So the first thing is to study the geometry, okay? Once we know the horizons and the light rings, what we do is to perform the ray tracing. And actually that was talking at all some moments ago. So here we are going to consider the Schwarzschild black hole. And basically the ray tracing classifies the light rays depending on the numbers of half turns, okay? Why? Because at the end of the day, we're going to have an accretion disk. So imagine that in this vertical axis, we have an accretion disk. This would mean that it will emit one photon from here, but also from here. So this is why we're counting these half turns, because a photon will be emitted here and reach us while we are here in this infinity far away. And also another photon can be emitted here and will do half turn and reach us, okay? So basically, this is done by tracing back the geodesic equation that it's written here. And this is done while we write the geodesic equation in terms of the impact parameter. Why? Because we are so far away that at the end of the day, these light rays are going to come as parallel to each other. So what we're going to see, actually, when we see the picture, it's the impact parameter, but not the radius of the geometry. I hope that this concept is clear because it's going to be used later on. So as I said, we classify the light rays depending on how many turns it does with the vertical axis. And as you can see here, is that we have different colors. So if we check this first color, it's green. And these are the light rays that only crosses this vertical axis once, okay? And this is what we're going to call the direct emission. Then we have the orange light rays that crosses two times, one here and the other one here. And we have the third case that you can barely see because it's very narrow, so the impact parameter range is so small that you can barely see, but it's these red lines. And actually, if you would be closer, it crosses three times. And the same happens, so we can split for the light rays that go outside the photosphere. That's this yellow dashed line that we can see here, or circle. And this is the horizon. This is for the Schwarzschild case. And then we have the same thing, but for when the light rays enter. So they pass this photon ring or this critical curve. And then we have black light rays that are the ones that go directly to this horizon. So what would we expect it that we will not receive lights coming from there at the end of the day. So usually for similar geometries as Schwarzschild, we only have three types of emissions: the direct, lancet, and photon ring. And basically what we do is store the different impact parameters with the different radius at which they cross. And then we can plot this in this type of graphs. And I have to say that most of the people doesn't understand them, but for me, this makes this gives us a lot of information. Why? So here we are plotting the transfer function, that it's basically the radius at which the light ray crosses. And what we can see is that basically the direct emission, which is the one that only crosses one time, so the photons that will directly come to us, has an impact parameter range very large. While as it goes more and more turns, this range is stretched. And that what does it mean? So that, for example, if we add on a creation disk at certain radius, we can only the disk can only meet in these different impact parameter ranges. So we will receive photons from this impact parameter to here, that would be directly coming through to us, and some small ones that are going to be the lancet or the second cut and the third cut. Okay. So what this means is that, of course, if this range is very small, this is going to be the diameter of the rings of the optical appearance. So if this is very small, this means that we will barely see it because it's very thin. Okay. And basically what we can also take from this is that the majority of the contribution will come from the direct emission, which is the one that is with more range of the impact parameter. But for example, if we change the position of the disk and we put it closer to the horizon, we can see now that there will be an overlap, because actually from the inner part, we can see still photons coming to us. So now it's time to talk about the accretion disk, and we choose the simple one. And actually it's based with the first paper about this topic of Gralla and collaborators. Okay, so basically the first thing that we assume is that the intensity that we observe, it's only dependent on the intensity emitted from the accretion disk. It's going to be corrected, but basically the shape it will be more or less the same. And then we also assume that emits isotropically and monochromatically, and it's optically and geometrically thin. Later on, we're going to enter on what does optically thin mean. And we also assume that it's almost it's perpendicular to us. So basically, if we come back to here, we are placing the accretion disk actually in this vertical axis. So that's why we were counting the cuts in this axis. And these are the three different models that we choose. Actually, these are ad hoc. So even though it helps us to understand which is the ring pattern that we're going to see, they are quite fake in the sense that it's not really physically of the accretion disk. Later on, they publish another one that it's more based on the physics of the accretion disk, but in these cases, it's not. It makes sense in the sense that in the three models, the peak of intensity is at the inner edge, where it should be hotter in a way, so emits more. And then we assume that it decays smoothly with different type of tails. So at the beginning, we used this configuration that this thinner peak it's in the ISCO of the object that we were studying, This second one was in the critical curve, and this other one was in the horizon if it was a black hole, or the wormhole throat if it was a wormhole. But actually, this can be exchanged. And in the last paper that we did, we already played with this. So as I told you, the observed intensity depends on the emitted intensity of the disk. And it's corrected by two factors. The first one is the redshift, and the second one is due to this optically thin accretion disk. What this means is that so when the photon is emitted and, for example, does another turn, it can cross again this accretion disk, and it will not be reabsorbed. But actually what can happen is that from the same point, the accretion disk emits another photon. So what would this mean is that we will have an additional contribution to the luminosity. And that's what this sum means. And this A is the time metric component and basically corresponds to the redshift. Okay, it's the redshift correction. So let's talk now about the results or the different geometries that we studied. And the first one is the black bounce, which was proposed with Simpson and Wieser. And basically, the fun thing of these families is that it allowed us to study the Schwarzschild case, the black hole case, and a wormhole, because at the end of the day, it has the same structure of the Schwarzschild, but the only thing is that now we have an extra parameter in the radial coordinates. So depending on this A, we can have that the wormhole throat gets until the horizon, or even after the photosphere. So this is what we plot here, which this is the potential that sees the light rays, and this dashed black one is the Schwarzschild case. And as we increase the parameter I, what we can see is that this is a non-transversable wormhole, and here we have a transversable wormhole. Okay? And we are going to check actually, so this black hole, the non-transversable black hole, and the transversable wormhole, sorry. And that's what we see. This is one of the cases for the later model. And what we see is that between the Schwarzschild and the black hole case, we can barely see a difference. And actually, even for the wormhole, the difference is very small. Why? Because at the end of the day, we are not modifying that much the Schwarzschild case. So what this means is that the photon ring or the light ring, it's placed at the same distance. So we don't have many room to play. But as you can see, I hope, is that this ring here is a little bit wider and brighter perhaps than the other cases, but it's almost nothing. So what we decided to do is, some months later, an extension or generalization of this appeared. And this is the generalized black bounce that was with Simpson and Wieser again, and some people from Lisbon. And in this case, the metric now is different. And actually, what happens is that depending on the parameter A, we can have a black hole with just one light ring, or traversable wormholes with two or one light ring. And if we check this case here, actually it's funnier, okay? So this is actually two types of emitted intensity profiles. These are the observed intensities, and this is what we would see. So from here, what we have is that we have the direct emission, which basically reproduces the profile of the emitted intensity. And actually, as you can see, it's the one that you can see better, as we mentioned at the beginning, almost. We have the lancet rings. Well, perhaps you cannot see, but they are pointed there. And finally, we have the photon rings that, of course, usually this impact parameter range is so small that most of them cannot be seen. But here we can already see that if we have two critical curves, actually it is quite different as the Schwarzschild case. And finally, the last geometry that we studied is this TA of the storm, but we took the non-rotating limit of this family. And actually, there are again several configurations that are interesting, but some of them then contain horizons. So we actually checked this orange curve in which we have a photon or a light ring and a stable light ring. So one is unstable and the other one is stable. And in this case, and I'm not going to really explain this, we can see that we have several colors. So, as I told you before, for a geometry that is very similar to Schwarzschild, we only have 3 types of emissions. But in this case, since we have this potential barrier, we have that higher emissions can also contribute not negligible. So this means that even the fourth cut with the vertical axis, it's already, the impact parameter range is non-negligible. And what this means is that after we put some accretions disk, we can see many photon rings. So that's the interesting part of this last type of geometry. So as we can see, basically, depending on the type of geometry that we have, this structure of rings is different. And to conclude, so basically, this shadow or this new optical appearance that we have, it's interesting to test the Kerr hypothesis. And actually, even though we can have problems disentangling these contributions, actually there are some features of the images that can be used to identify these objects that are non-Kerr. And finally, and this is regarding the accretion disk model, we use a very simple one. But actually, since it is a little bit ad hoc, it can also contribute to this tangling of these two contributions. So we need more precise models. And the problem is that usually we use this general relativistic magnetohydrodynamics simulations, but they are also very computational demanding. So I think that in the near future, it would be good to have some kind of toy model, but actually based on this kind of simulations, but in a very or much simple way, so that we can trust this. Because, and perhaps I'm going too far away, but these models of Gralha, they are very tuned to what they see in the EHT collaboration. So if we add a different type of geometry, this would mean that we are spoiling this fine-tuning in a way. So thank you very much.
Okay, thank you very much for the talk. So, time for questions. Okay, Arol, please come forward. And the next person who wanted to ask something on the back can also come forward and sit there.
Thank you for the presentation. I have a question regarding the generalized black bounces. So what's the new feature that adds these new peaks in the intensity? So in the next slide. So what's the feature, or what's the novel feature that introduces these novel peaks in the observed intensity? Is there any additional light ring there, or something else?
So actually, as I was saying, I'm here only plotting this case here in which we have two critical curves. So, and what happens is basically that we have, well, here we, wait, let me, because I I don't have it here. So uh, the question was that if there were two. Yeah. So actually, it's because we have two light rings. Yeah. Yeah.
So in the case of the wormhole part of the black bounce, so you have this extension in the radial coordinate. So now the radial coordinate can goes to plus infinity to minus infinity. Did you consider accretion disk in the other side of the truth? What would be like the qualitative difference? This could be, I mean, interesting to compare with the black hole case.
Yeah, actually, that was something that we wanted to check. But so back then, there were many works coming out. So we were kind of on a rush. But the thing is that, of course, if there's a wormhole and it's traversable, if we put an accretion disk in the other side, you will see illuminated. So it's not going to be completely dark, but it will have some light coming out.
Okay, so more questions, please, Kyle.
Hi, thank you for the very nice presentation. So, so you comment about the GRMAG simulations, but in my opinion, in this case, I think it's more like a direct. So, in my mind, I kind of expect like a profile to have a peak near the ISCO. So, what the thing that I think is more physical for the disk is like what the one that you show the peak in the at the ISCO, right? Because for instance there is no support for orbital motion that are stable beyond the ISCO, right? So you kind of expect something like this disk profile. So is there any difference? So why to consider like a peak of radiation at the horizon? Or because I think it's interesting because you end up showing that despite the models being very different, they show very similar profiles. Because so one thing is like shouldn't we look for more models, even just looking at the geodesic structure? Like, it was one question that I had to Haroldo also is was whether those universe they have support for like time-like geodesic, because in the end, those are the ones that they're meeting, right? Or
So actually, I don't recall that much the argument, but actually, the ones that DHT is more favorable to explain this is that the inner edge is at the horizon, actually. Yeah, not in the ISCO. And I wouldn't remember which is the argument, but I can search for it and I can send it to you. But for sure, it's for supermassive black holes. I think that when it's a stellar black hole, then the argument is different, and I think that then it can be the ISCO. But for supermassive black holes, it's in the horizon.
because I would say like you have like stable orbits, and then so for the disk that falls into the horizon, you could have emission there, but it stays for a very short time. And at the horizon, I would say so. This is the profile in the proper reference frame, right? But if you add the head shift, this part vanishes, right? The part near the horizon. Okay, okay, I see. I see. So you can have like emission peaking at the horizon, but in the end, because of their head shift, I would suppose that those doesn't show.
Perhaps not very close, but you can still observe them, actually. Yeah.
Okay, so more questions. No? Okay, so let's thank Mercè again.